Welcome back. We have started talking about solving games. What does it mean? That we want to figure out what happens in a strategic interaction. And our life becomes a lot easier when each player has a dominant strategy. Because if each player has dominant strategy, they would use it in that strategic interaction and we can obtain what would happen in that strategic interaction. But the problem is that in all games, not all players will have dominant strategy. In fact, in most games, none of the players will have dominant strategy. How to go about solving those games, how to go about obtaining outcomes in those games. So, in this video, we will make some progress in that direction, what to do. So, let us take a look at this game. What we have two players and player 1 has UMD, 3 actions available, player 2 has 3 action available, LCR. Let us check whether one of the action is dominant action or not. So let us check first U and M. U opposed to L, when player 2 is playing L, U gives 0, M gives -1, so L is better. When player 2 is playing C, then U gives 1 and M gives 0, so this is better. And when player 2 is playing R, then U gives 1 and M gives -1, so U is better. So no matter what player 2 is doing, U always gives more to player 1 in comparison to M, so we can say that U dominates M. So if you could also dominate D, and of course U is dominating here strictly, if you could also dominate D strictly, then it's very easy to say that player 1 will play U. Is it the case? So when player 2 is playing L, U is giving 0, D is giving -1, still this is more. When player 2 is playing C, U gives 1 but D gives 2, this is more. And therefore, U is not a strictly dominant strategy. That we have to be careful about. How to go about solving such games? Let me remove these tick marks. But as we have figured out that if a player has the strictly dominant strategy, then player must be playing that strategy. We can also say that if player has a dominated strategy, that player would never use that strategy. In this game, player 1 can decide not to play M ever because U is there, which gives always more than M. So we can say that player 1 is never going to play M because M is dominated by U. Remember what we have assumed, that all players know what game is, all players are rational. Player 1 knows that player 2 is rational, player 2 knows that player 1 is rational. We still cannot remove M from this game because player 1 is not going to play, but does player 2 know that player 1 is not going to play M? Yes, because we have assumed in common knowledge, we have assumed way more, because player 2 knows that player 1 is rational and therefore in presence of U, player 1 will never play M. And so therefore we can remove M from this game. Not only 1 is not going to play, 2 also knows that 1 is not going to play, therefore M can be removed. So now player 1 has only 2 strategies and player 2 has 3 strategies. Can we remove anything further? Let us look at for player 2, L for player 2 does better than C when player 1 is playing U. 0 is more than -1. Again, I have to repeat, the first number is for player 1 and the second number is for player 2. And player 2 chooses column, player 1 chooses row, and therefore we are doing column wise comparison. And so 0 is more than -1, this is better, and 1 is more than -1, so this is better. So clearly in this reduced game, it's also possible that in larger game also, but we don't need to care about larger game. In reduced game, player 2 is never going to play C in presence of L, and with the same logic, not only player 2 is not going to play C in presence of L, player 1 also knows this fact that player 2 is not going to play C, and therefore this C can be removed from this game. So now each one of them have two strategies. We can we do further reduction? Of course, for further reduction we need more information. So if I write here, this is the further reduction. First let us reduce and let us look at the logic later. So here we have 0 0, 1 minus 1, minus 1 0, 0 0. So 0 is more than minus 1, 1 is more than 0. So U does better than D in the reduced game. And 2 also knows that U does better, but we have to go one step further, because this we have reached, this game has been reached by second level of logic. Not only player 1 knows that player 1 is rational, player 2 is rational, this is level 1. Level 2 is that player 1 knows that player 2 is rational, player 2 knows that player 1 is rational, and therefore M and C have been removed. Now the third stage, because through this player 1 knows that player 2 knows that player 1 is rational, therefore they will be able to remove these, and now in the next stage we are U is better than D, so D can be removed from here. And further, because 0 gives more than minus 1, so this can also be removed. So you are left with U comma L. This is called iterated elimination of strictly dominated strategies. Okay, we are eliminating the dominated strategies iteratively. As we remove, we are getting a smaller game. In a smaller game, we check whether a strategy is getting or an action is getting dominated or not. If it is strictly getting dominated, we would remove it. The logic is very simple, that players know that other player is rational, and therefore the other player is not going to use that action or a strategy, and therefore we can successfully remove uh, such dominated strategies. And we may be left with, in this game we are lucky that we are left with unique outcome, that is U comma L. Player 1 should be playing U, player 2 should be playing L, and that would be the outcome. Let me repeat again, the reason M and C were removed, because each player is rational and each player knows that the other player is rational. Why did we remove D? We removed that each player is rational and each player knows that other player is rational, and each player knows that other player knows that each player is rational. That's the third level of argument required to remove. As we move further and further, higher level of requirement, higher level of requirement in common knowledge would be required, and therefore right at the beginning in common knowledge we have assumed that everyone knows X, everyone knows that everyone knows X, everyone knows that everyone knows that everyone knows X, and so on. So that's the way we proceed. We can look at some other examples also to understand it better. How can we do the removal here? Here it's simpler game to begin with. Player 1 has only 2 action, player 2 has 3 action, and it so happens that if you look at for player 1, U doesn't dominate D. Why? Because when player 2 plays R, D gives more than U, and therefore U doesn't dominate D. D also doesn't dominate U, because when player 2 plays L, then D gives 0, U gives 1, so U doesn't dominate. So we have no help here if we just want to use dominant strategy. How about dominated strategy? We have already shown that U doesn't dominate D, D doesn't dominate U. How about for player 2? M clearly dominates R, because 2 is greater than 1 and 1 is greater than 0. So no matter what player 1 is playing, whether player 1 is playing U or D, M always gives more than R. So M dominates R or R is strictly dominated strategy, we can remove this. Next round of argument would be, now if you pay attention in this reduced game, that U strictly dominates D, because let's move out of game, and for a minute of course we will have to take help from the game also, that player 1 is rational and player 2 is rational, and player 1 knows that player 2 is rational, therefore player 2 is never going to play R, and player 2 is rational, therefore player 2 is never going to play R, so R has been removed. Further, when it is removed, not only player 1 is rational and player 1 knows that player 2 is rational, player 1 is rational, player 1 knows that player 2 is rational, player 1 knows that player 2 knows that player 1 is rational. So after the removal, now U strictly dominates D, and therefore this D cannot be played by player 1. And now similarly further with the further logic, this can be removed and you are left with U comma M, and the outcome here is going to be U comma M, and payoff to player 1 is going to be 1 and payoff to player 2 is going to be 2. So that's the way we will obtain. Here is a much more complicated example. The difficulty level is increasing tremendously here, but nevertheless it's a fun game to do. So I would request you to gather some friend or family member and do this game. The game is very simple. What we have to do is that we have to guess, each one of your friend will have to guess the 2/3 of the average of all guesses. It means everyone is guessing and the average would depends on everyone's guess, and therefore 2/3 of the average will also depends on everyone's guess. So the rules are very simple. You tell them to choose a number between 1 and 100. They can in fact also choose 1 as well as 100 or any number in the middle, whole number, to keep the story simple. Even with fractional number there is no problem, but let us keep it simple, and 1 to 100 they can pick. So how many choices do they have? They have exactly 100 choices. They have 100 different actions they can take. You can decide if you are in a mood to splurge, keep a surprise gift for the family member, friend, colleague whose guess is closest to 2/3 of the average of the number chosen. Ask them to write down their answer as well as their name, so that then only you could figure out that who has given, and hand it over to you. Wait, tabulate it in an Excel or anywhere, calculate the average, then calculate the 2/3 of the average. Let us say there are only 4 people and they have given you 25, 50, 75 and 100. How much is going to be the average? The average is going to be 62.5. How much is going to be 2/3 of the average? 125 by 3, roughly 41.667. Who is closest? This person wins the game. He is closest to 2/3 of the average. Just for example, I told you that this is the way you could do, and you can give him a Kit Kat or something, or her Kit Kat or something. You can, just for so that people take it seriously, you can pre-announce it. Now let us look at the way we can solve it using iterated elimination of strictly dominated strategy. People can pick a number, and I will not solve it completely, just we will understand. People can pick a number 1 to 100. So these are the actions available. If you have 10 people playing, you cannot make table, you cannot have access to techniques to make 10-dimensional table, so that's completely out of picture, but we can still argue. Let us say, for example, one person should argue that if everyone is guessing 100, how much is going to be the average? Average is going to be 100. If everyone guesses 100, average is 100. How much is the 2/3 of the average? The 2/3 of the average is 66.67. Okay, so there is no point guessing any number which is above 67, because 2/3 of the average is never going to be higher than 66.67, and you want to be closest to this. So what we can say, that any guessing any number 68 to 100, they are strictly dominated. Okay, so you can remove, for each player you can remove, you have not played the game, you are arguing in your mind. So in the next, now if everyone is rational, then everyone should remove these numbers. You have a reduced game in which people should be guessing only 1 to 67. What would be the average, maximum average possible? 67. What would be the two-third of the 67? It's going to be 44.33. I hope I am right, I am not, so again, there is no point guessing any number above 44, because in the reduced game, all the guesses above 44 are strictly dominated. So keep doing this argument and figure out what should be the outcome, how much people should be guessing. That's the task number one. That's theory. Now in practice, you can see that whether they have really guessed that number or not. So of course, let me tell you that you would be disappointed. They won't be guessing the same number that's coming from your solution. They would be guessing wildly different number. What is the problem? I don't know what is the problem. Perhaps they didn't think it through. They were not in, being in fine using their calculation power. Perhaps they didn't take it seriously. We don't know. But if you have a serious gift there, a big, large enough gift there, and people take seriously, and you repeat the game twice, thrice, not exactly with the same people but different people in the mix, and pretty soon they realize what the game would be, and you would see their guesses are coming closer and closer to your theoretical number that you are coming up with all the person. So this is another example of iterative elimination of a strictly dominated game. As we are talking about eliminating strictly dominated strategy, can we eliminate weakly dominated strategy? Think about it for a minute. It's not a bad idea to eliminate weakly dominated strategy. Look at the game here. Compare, there are two stores, they are selling items, they can have high price, low price, they can match the price with other. You see that for store A, high gets weakly dominated by match, because 10 is equal to 10, here 10 is equal to 10, 5 is greater than 2. Again, let me emphasize, when I am comparing for the row player, I am doing row wise comparison. When I am comparing for column player, I am doing column wise comparison. Okay, that should be clear. Why? Because store can choose different columns, store B can choose different columns, store A can choose different rows. So that's what you should be aware of. So if we allow to eliminate weakly dominated strategy, then high will get eliminated, and similarly high here will also get eliminated by the same process. Store B, we will have the smaller game, and in this game also, now both players have weakly dominated strategy. Low is getting weakly dominated now, so low can be eliminated, and we would be left with match. Okay, this would be the outcome. Before I talk about there is a problem with weakly dominated strategy, one has to be extra careful. Let me talk about something what we call dominance solvable. So we are talking about iterated dominance in the large game. We are removing the dominated strategy. Further, we get the reduced game. In that, we still get some dominated strategy or action. We remove them. So we are doing it iteratively, and we are repeating the process. Before we proceed, let us also look at this game. What happens in this game? What we have here is that you we can say that you dominates, u strictly dominates G. So 0 is greater than -1, 1 is greater than 0, 1 is greater than -1. So this can be removed. And similarly, R for player 2, row player, column player, R dominates M. 1 is greater than -1, 1 is greater than 0, 0 is greater than -1. So this can also be removed. So you are left with a smaller game. You have U, B, L, R. Here is 0, 0, 1, 1, -1, 1, 2, 0. Does U dominate B? It doesn't, because 0 is greater than -1, but 1 is less than 2. So U doesn't. And similarly, B doesn't dominate U. How about R and L? 1 is greater than 0, but here 0 is greater than var. So now we cannot proceed further using the technique that we have learned. What we will see is still this technique is useful, that rather than solving this game, now we need to solve this game. So it has reduced the complexity. Nevertheless, not all games could be solved using the technique that we have learned. So we say, if iterated elimination of dominated strategies or iterated elimination of dominated actions lead to all but one action for each player, then the game is called dominant solvable game. If we use iterated elimination of strictly dominated strategies or iterated elimination of weakly dominated strategies, and it leads to one action each for all the players. So basically we get the outcome, then we call the game dominance solvable. Clearly this game is not dominance solvable. So before we close this video, let us look at the problem that we have with iterated elimination of weakly dominated strategy. Here is a game. We have two players, up, middle, down, left, right. And let us, we will do it twice in two different ways. Okay. We will have the same game here, UML, UMD, LR, 1, 1, 0, 0, 1, 1, 2, 1, 0, 0, 2, 1. So exactly. So now what we see here, we see that M weakly dominates U. So we can remove U. We have a reduced game in which player 1 has only MD and player 2 has LR. What we can do here now, we see that R weakly dominates L. So we can remove these. We are left with two possibilities where player 1 can do M or D and player 2 can play R. Both, we may not know whether this will happen or this will happen, but we know in both cases player 1 will get 2 and player 2 will get 1. Now let us change the order of elimination. Rather than eliminating U, as U is weakly dominated by M, if you pay attention, D is also weakly dominated by M, because here 1 is greater than 0 but 2 is equal to 2. So let us eliminate D because it is weakly dominated by M. So we can remove this. Now in the reduced game, what we are getting, that each player has two strategies, and in this reduced game, L for player 2 dominates R, because 1 is greater than 0 and 1 is equal to 1. Here weakly dominates R, but we are removing weakly dominated strategy, so we can remove this. Again, we don't know whether this box is going to happen or this box is going to happen, whether U comma L will happen or M comma L will happen. We don't know. Another thing that we should notice, that this game is not dominance solvable, because no matter what is the order of elimination, it's not leading to leaving only one action for each of the player. Player 1 has two actions here and one action for player 2. Here also player 1 has two actions, so it is not dominance solvable. Nevertheless, we are getting very, these two outcomes are not even coming there. What is happening? So I want to say that iterated strict dominance is path independent. It doesn't matter the order that you use when you have strict dominance. But the problem is when you have weak dominance, then it becomes path dependent. In case of elimination of strictly dominated strategy, the elimination process will always terminate at the same point, whether with one action each for all the player or many more action for all the player. As long as you are eliminating only strictly dominated strategy, it will always lead to the same situation. That is not the case with elimination of weakly dominated strategy. That's why we have to be careful. Given the knowledge that we have as of now, we won't be able to resolve what should we do, but we are going to learn more solution concept that will help us automatically understand what happens in these scenarios, and we will be using these techniques later on, just a way to reach to solution quickly, nothing more than that. Our most important solution concept is Nash equilibrium, which is next. See you in the next video.